All right, let's look at how to select values for capacitors now. So we can, the title of this is, it's up above there, but I'll write it again. Like selecting cap values for low frequency. Cutoff. All right, so our design objective here, let's write that down because this is really important, is to place the lower 3 dB frequency FL at a specific value while making the cap values as small as possible. You want to keep them small. Small as possible. Okay. We're going to refer to the common emitter. We had gone through the common emitter example using the method of short circuit time constants. It's the example we went through in the lecture prior to this. So we said, let's see, for common emitter, BJT, CE, that emitter bypass capacitor, that's C little e, we said for a comma, C little e usually sees the lowest of the 3 resistances. Okay, so you can pick the value of C little e, that bypass capacitor. So its contribution to FL is dominant. So we want to look at how to do that now. So let's look at an example. Okay, and in this example, let's say we want to select appropriate values for CC1, okay, coupling capacitor, CC2, coupling capacitor on the other side, and C little e, the emitter bypass capacitor for a CE, that's big C, big E, amplifier. Again, when you see CE, that's a bipolar junction transistor, BJT amplifier, CE amp, that. Okay, let's look at some specs. So you can refer back to the diagram. We had it drawn earlier, but we can say RB. That's that combined. If it's voltage divider biased, right, that's RB1 in parallel with RB2, the way the book, again, the notation the book uses. So let's say that parallel combination is 100 k ohms. That's the base equivalent base resistance. Okay, RC, collector resistor, is 8 k ohms. RL, our load here is, in this example, is 5 k ohms. The internal resistance of the source is 5 k ohms. RE The emitter resistor is 5k ohms. Let's say beta is 100. Transconductance is 40 milliamps per volt. And our pi is 2.5k ohms. And again, we said our pi was the, that's the resistance. It's a given value at the base with the C and E terminals shorted. Okay, and let's just say FL here is spec'd. We were looking for 100 hertz. Okay, so new page. We just got to go through the capacitors, just like the example we just did. We're going to put some numbers in now. All right, let's make this a little smaller. I don't know why it's doing this. All right, so we can say 4 CC1 for that first coupling capacitor. We just went through this in the previous video, but we got our sig here. We're putting some numbers in. We're told that's 5k ohms. CC1 is what we're looking for. Don't know what that is. RB given 100k ohms. Our pi given 2.5k ohms. Okay, so we can calculate the resistance seen by CC1. Again, it's just the series parallel stuff, so we can call that RC1. We said that was equal to, or that's going to be equal to, looking at the circuit. We don't have to refer back. It's going to be RB in parallel with our little r pi plus our sig is 100 k ohms in parallel with 2.5 k ohms plus 5k ohms. You get 7.44 k ohms. Okay. For CE, let's calculate. We're going to calculate the resistances first. How about that? And it's the way the book runs through this stuff, so we'll try to follow the same procedure. So we're going to calculate all the time constants and or the resistances. Then we'll calculate the time constants and take the reciprocals to find the low frequency cutoffs. So let's do for CE the bypass capacitor next. Okay, and this is going to be the resistance seen by CE again. So referring back to our previous video lecture, little segment. Let me just draw this and we'll put some values in. What do we got here? I think I'll write these in red just so they stand out a little more. Okay, up here, this resistor value, we've got RB in parallel with our sig. Okay, divided by beta plus 1. So you got, what, 100k parallel with 5k. Okay, divided by 101, beta is 100. 100 plus 1 is 101. We get 47.1 ohms. Okay. Little re is 1 over the transconductance. Okay, that's given, so it's 1 over 40 milliamps per volt is 25 ohms. Okay, and RE is given, that's 5k ohms, and CE is what we're looking for. Okay, so our CE Switch back to blue here. Again, RCE is the resistance CECs with the other two capacitors shorted. So RCE is going to be what? RE in parallel with the 47.1 ohms plus the 25 ohms. So that's 5K ohms in parallel with 72.1 ohms, 71 ohms. Okay, so we've got, I probably should have boxed this. We've got the resistance that C1 sees, RC1, and we said that was 7.44 K ohms. We've got RCE, that's the resistance that CE sees, that's 71 ohms. New piece of paper. Let's do CC2. Okay, again, this is the resistance that second coupling capacitor sees with the other capacitor shorted out. So we can draw our equivalent circuit here. We've got RC, 8K ohms. We've got CC2, the mystery capacitor in this case. We've got RL here, 5K ohms. Okay, and we can say RC2. Again, that's the resistance that CC2 sees. Is just these two resistances, RC and RL, in series. So we've got RC plus RL, 13K ohms. Okay, so we've calculated our resistances. Okay, next, if we select CE, so it contributes 80% of the value to our cutoff frequency, and this is something that I missed. But this is typically what's done. If CE is going to be the dominant pole or set the dominant frequency, you set it so it contributes 80% of the value to omega L. Let's say this, if we select CE, so it contributes 80% of the value. And again, this is pretty typical when these things are being designed. Of the value of omega L, we get CE, and we do a conversion. We do a conversion to frequency. We can say 1 over CE times 71 ohms. Okay, it's going to be equal to 0.8 times 2 pi times 100 hertz. Okay, you follow that? So it's 1 over the time constant, 80%. Okay, this 100 hertz now is FL. 2 pi is just in there for the conversion, and 0.8 is the 80%. So you can chug through this thing. You can solve. You'll get a CE value of 28 microfarads. Okay, so that's one answer. Now let's look at CC1 and CC2. We'll do CC2 first. I don't know why, but that's the way. That's the order the book follows, so I'm doing the same thing. Next, let's select CC2 so it contributes 10% of FL, of the value of FL. Okay, so it would be 0.1 times 100 hertz or 10 hertz. See what we're doing here? We're setting up, we've set up CE. We're saying CE contributes 80% of the value of the cutoff frequency. Now we're saying we want CC1 and CC2 to be reduced. Okay, so we're setting those up to contribute. If we select CC2, we'll do CC2 next, to contribute 10% of FL, comma, let's say value can be selected 1 over CC2 times 13 k ohms, which is the resistance that we calculated that CC2 sees, is going to be equal to, now it's 0.1, 10% times 2 pi times 100 hertz. Solve for CC2. You get 1.2 microfarads. Okay, and new paper or new page, we can do the same thing for CC1. If we select CC1 to contribute 10% of FL, so we're minimizing the contribution of these coupling capacitors on purpose. Okay, so we can do the same thing. We can say 1 over the time constant, so it's CC1. We don't know the value of that. We said that the resistance that CC1 sees when the other two capacitors are shorted out, we already calculated that. We got 7.44 k ohms. It's contributing 10%, so 0.1, we're doing a conversion, times 2 pi, times 100 hertz. We get a CC1 of 2.1 microfarads. Okay, so this method works pretty nice. In practice, one more note here. You're probably not going to find a 2.1 microfarad capacitor. In practice, the 3 caps would be selected from standard value caps, basically the stuff that's in the drawers in the labs. Those are pretty typical standard values. The stuff that's stocked in the labs. The 3 caps will be selected from standard value caps that are closest to these calculated values, while ensuring that low frequency cutoff is less than or equal to 100 hertz. Okay, we could have also calculated, or we can also calculate the frequency of the 0, introduced by our dominant capacitor, so we can say by CE. Okay, so we can say FZ, 0 frequency, can be 1 over 2 pi times CE times RE. Okay, we went through that derivation earlier, but you do that, you chug in You know what the value of CE is right now. You get 1.1 hertz. Okay, and that's pretty far. Let's just say, let's make a little note here. This is very far from FL, 100 hertz, and has insignificant, as far as we're concerned, at this point in the course, insignificant effect. And there you go. So